Dear friends, hearty welcome to the third day session of the 7-day crash course on Focus on TIFR GS 2025. Our resource person, Mr. Lalit Thuwal, research scholar, IISc Bangalore, is ready. So without any delay, we can directly move to the session. Welcome everyone to this program. Welcome, Lalit.
So I'm going to present my screen. Let me know if you can see. So yesterday at the last, I said that you may watch the solution of this one and this one, right? So now I start with this question. So this question says that there is a uniformly continuous function f from this interval, okay, r positive to r positive, such that this reach converts, okay, because fn is non-zero, so each term is here well defined, okay. So to see this, I'm going to let you know a very good result about the uniform continuity of a function. Okay, so that will help you to solve the problems in exam, not only in TFR but also in other exams. Okay, that result is very helpful to determine whether sometimes whether a function is not uniformly continuous. I mean, it's useful to determine sometimes that function is not uniformly continuous. Okay, and also I mean, whenever you have a uniformly continuous function, then you can use it as you will see that how you can use it, okay, in next two questions. So see, what is the result? Let me write it here. Suppose f is okay, r to r, a uniformly continuous function, uniformly continuous function, there exist a and b greater than 0 such that mod of fx less than and equal to this. Okay, so I will not prove it here because I don't have that much time, but if you want to see its proof, then you can watch in the TFR 2024 playlist in the YouTube channel, okay, what I told you. So there is a question number 19 in part B where you can see that how to prove it also, okay. So see, you have this for this is satisfies if you have some interval here also, okay, in place of r here, okay. So if you have some interval, then it is also true. So see, what is asked to us, that is this convergent? Now see the I mean, how can we use this result? Okay, so we have mod of fn is less than and equal to a mod n plus b for each n, right? Right. Since f is a positive function, it takes non-negative, I mean, always positive value. So I can write mod fn equal to fn. Yes. So we get this, and mod n equal to n. Okay. So from here we see that one, or we see that this happens, right? This holds for all n. So all n. What can you say about the now convergence of this reach? Do you know some tests? Raise your hand if you are able to see now. Okay, very good. So, right. So, Sagnik, what do you think that will this converge?
No, it won't.
Why?
Because if we do a comparison test with 1 by n,
Okay.
then
Right.
it
It does not converge, right?
yes.
Okay, good. So this it follows that, right? This a right? Considering the sequence of partial sum, then taking n tends to infinity, we get this. So on the in this side, we see that this series is divergent, right? Because 1 by n is divergent, and I mean you can compare this series with 1 by n. There's a limit form of the test, right? So you will see that this series is also divergent. So what I said convergent. So it is divergent. Okay. So it is divergent, then it must be divergent, right? Because its sum is greater than this, greater than or equal to this. So, right. I should say that directly its limit is infinity. Okay. Not like greater than equal to this. So the sum is not in R. So, right. So in this way, we found that this for any uniformly continuous function, this series never converts. Okay. So this is a false statement. Okay. Next question. So now why I'm letting you know this result, why this is so, useful, because this is a question of, I think, 2019 or 2018 exam, and this is a question of 2024 exam. Okay. So uh, can you yourself apply the above result and determine whether or not this statement false? Okay, so go back, and if I ask you some question, I will come back to this later. So I ask you some question. Okay, answer me. Okay, so suppose that F is R to R uniformly continuous. Okay, you see, then prove that limit x tending to infinity fx x to the power x square, just x square, say mod of fx over x square equal to 0. So can you prove it? You can use the result what I stated just ago, right? Yes. So see, we have from the above result, we have this, right? So if x is not equal to 0, then we get this, right? If x is not equal to 0, I can divide by mod of x square. So I get this. So for x not equal to 0. From here, we immediately see that what we want, right? As x tends to infinity, then this side will go to 0, and this is already 0. So we get that this limit is 0. In place of x square, if you have x cube, sorry, if you have x4, x100, anything, right? Mod of x to the power n, mod of x to the power n, x square, x cube, x4, then you will get this limit is equal to 0. Okay, right? So now, yeah, you can try to think about this question. I want that yourself should think about it, and I will give you 1 minute. Okay. Not because that it should be solved in 1 minute, just because we have to keep in mind that we have only 1.5 an hour, right? 1 plus half an hour. So, okay. So, Yeah, try to think. You can do it, okay? Okay, so let me tell you that how do you solve it? So you have given that f r2r is a uniformly continuous function, right? So you have this, okay? Mod of fx over x to the power 100 is greater than equal to 0, and this is less than or equal to by the above result, okay? X to the power 19 plus, I can just say that because I have already told about it. So I can say that limit mod x tends to infinity equal to 0, right? Because I have already explained it why. So see, then by definition of limit, you can make this less than 1, right? Less than 1 for sufficiently large values of mod x. So for all x satisfying mod x is greater than m, right? This is the definition of limit, infinite limit. So from here what we get that mod of fx is less than x to the power 100, and this right, everyone knows this, that mod x is greater than or equal to x. So I have used it here for all x satisfying for all x in. So when we say that mod of x is greater than m, what does it mean? It means that mod of x should not lie in this interval, right? Suppose this is your minus m and this is your m. So when we say that mod of x is greater than m, what does we mean? So we mean that either x cannot lie in this interval, right? If x lie in this interval, then mod of x is must be less than or equal to m, right? So for all x which does not lie in the interval mod which does not lie in this interval, right? Okay, so in this way I get that this statement is true. So that's the power of that result. Okay, we have solved 2 questions. Okay, the similar questions may appear in the next exam also, so you may try that result, and that is very useful because see, suppose you have given asked that e to the power x is uniformly continuous or not. For a moment, suppose that, okay, then you don't want to apply some sequence test. Okay, you need not to apply that. You can, because you see that this limit, okay, this limit is not 0 as x tends to infinity. So this must be non-uniformly continuous function on R, okay? And this result might be helpful to determine that some function is not uniformly continuous as you apply in e to the power x. But one thing keep in mind, one thing to keep in mind, that please do not assume that f is uniformly continuous. If you have a function which is continuous and satisfying this, okay, then the function need not be uniformly continuous. So keep that in mind, okay? So, but if the function is uniformly continuous, then it will satisfy it. Okay, so let me move to the next question. Now, this is a question from NBHM, not from TIFR exam. This because the group Q by Z is, the questions from this group are asked in every exam. Okay, so it is very important. Yeah. So, do you want to say something? Or someone is muted? Unmuted, I think. Okay, see. So see, let's solve this question. And after this question, I would be asking you a very interesting question about the isomorphism of groups. Okay, I will ask you that 2 groups are isomorphic or not. So you might have used, whenever you did given 2 groups that suppose G1 and G2, and you are asked that whether or not they are isomorphic. Suppose you want to prove that they are not isomorphic, then what do you see? The number of elements and etc, right? But here you will come to know something interesting, okay, by which you can decide that the two groups are not isomorphic. Okay, so after this, I will ask you that question and you will answer me. So that's very interesting. Okay, so see, now let me solve this. What does this question say? That for n a positive integer, this q modulo nz be the quotient group of rational numbers q under addition by the subgroup nz. Okay, so for each of the following statements, state whether it is true or false. Okay, so solution. This is q modulo nz, say g. Okay, so every element of q modulo nz is of finite order, right? This is very easy. See, let me show you how to do it. So pick some element from this group. Okay, this will look like this. This is a coset. So P by Q. Okay. So, oh, wait, give me 1 minute. Yeah. So see, suppose this is any element. This is any element of the group. But if we can assume that Q is positive, right? If you have a rational number, then you can always assume that Q is positive, right? So I add it Q times. Okay. Then what do I get? I get it is equal to P plus nz. Okay, but P rather I will add it nq times. Okay, so I get np plus nz, but np lies inside this group, so this comes out to be nz, which is the identity of our group. This, right? This group has identity this. So what does this mean? This means this element has order dividing nq, or we can say that this has finite order. Has finite order. So we have seen that any arbitrary element of this group has finite order. Hence, we write here it's true. Okay. Now come to the next one. There are only finitely many elements of Q in Q modulo nz of any given finite order. Okay. Suppose that you are asked that how many elements are of order 10 in this group. Okay. So let me tell you, for the group Q modulo Z. Okay, then I will because first let me solve this one D. Okay, then I will come back to this. Okay, so D, it asks that Q modulo 2Z and Q modulo 5Z are isomorphic. Okay, so see. So how many of you know this, that if phi is any automorphism of Q, okay, or any homomorphism is of this form. Homomorphism, this is a result, okay, and useful. So then phi of x is equal to Rx, okay, for some fixed R in Q. So any homomorphism of Q looks like this. So what does this mean? If your R is non-zero, then any homomorphism is an isomorphism, right? Because this type of function is onto n1, right? So see, now you see that, okay, Q. So I have a function which sends x to 2x, okay? This is a homomorphism, right? Is an isomorphism. So there are other ways to prove it also. Okay, you can directly define a isomorphism by observing that which elements should go to where. So that will work. Okay, these are isomorphic, but I'm going to let you know a general way, which will prove that all Q modulo NZ are isomorphic. Okay, these all groups are isomorphic. Q modulo Z, Q modulo 2Z, Q modulo 3Z, everything is isomorphic. So what I'm going to do, I'm going to prove that suppose you have given Q modulo NZ. Okay, so I'm going to prove that this is isomorphic to Q modulo Z. Okay, so all Q modulo NZ are isomorphic then. It follows, right? So C is an isomorphism. Then it will induce and it sends Z to, what is the image of Z under this isomorphism? That it will send to NZ, right? So we get, so you know that you must have seen this, that if two groups are isomorphic, then they are equal from the point of view of abstract algebra. Okay, so see, you have this, right? So this must be isomorphic to Q modulo Z, the image of phi Q over image of phi Z, right? Because phi is an isomorphism, but image of phi is again Q, the image of Q, and image of Z is NZ. So in this way, we get that Q modulo Z is isomorphic to Q modulo NZ. Okay, so all groups Q modulo Z, Q modulo 2Z, Q modulo 3Z, all these are isomorphic. Not only Q modulo Z, 2Z and Q modulo 5Z. Okay, so this option is true. Okay, so now option C. What do you think about option C? That this is true. It says that every proper subgroup of Q modulo NZ is finite. So what do you think about it? Is it finite, or we can give some infinite subgroup also? I think you, if some of you would tell it, it's good. Okay, or if you want to tell it, okay. Do you know some infinite subgroup of Q modulo Z? Now you just have to, you know, think about Q modulo Z. Don't need to think about that Q modulo NZ, because all these are isomorphic. Okay. Yeah. Yes. You like to tell? Someone is unmuted, I think.
Sir, m by 2 to the power n, the subgroup containing elements in the form m by 2 to the power n.
Okay, very good. M by, okay, let me write, okay, 2 to the power n plus z, where m and nz, m and n are integers, right? It is a subgroup of Q modulo Z and it's infinite, right? You can verify it, it's infinite, okay? Because it has elements of order 2 square, 2 cube, 2 to the power 4 dot dot dot, and so on. You can verify that, because no, you can just see it. Okay, don't need to verify. See that whenever m is you take some odd number, right? Say 3 and 2 to the power 100, then this is an element of 2 to the power 100 of order 2 to the power 100. Okay, in the same way you get a element of 2 to the power 101 and so on. So this is an infinite group, but this is very interesting group. Okay, so do you know what is the interesting property of this group? It has very interesting property.
Every subgroup of it is a finite order.
Finite order and cyclic.
Yeah,
right?
yeah, cyclic, yes. But
Finite
it is not
cyclic.
cyclic itself.
Yeah, it is infinite non-cyclic, and its every proper subgroup is finite cyclic or just cyclic. Finite cyclic, right? Okay. So every proper subgroup is finite. Okay, this is very interesting. You should keep this group in mind, because I have seen the questions where it is asked in TIFR 2018 that if H is a group whose every proper subgroup is cyclic and H is an infinite group, then H is cyclic. So that is not true statement. You can, I mean, this is the counter example for that question. Okay. So very good. Uh, that's why this is true. Okay. So there are only finitely many elements of elements in Q modulo NZ of any given finite over. Okay, let me leave it for you. So there are exactly, suppose you have given n, suppose you have given some positive integer, say m, then there are exactly 5m elements of order m. Okay, so let me leave it for you. Just try to see that which element has order m in Q modulo Z. Okay, then you will immediately find that. So some element of the form, like suppose m is a positive integer. Okay, then the here you put those R1, R2, M, but this is coset. Okay, these are just coset. I'm not writing R1 modulo R1 by M plus Z. Okay, and that's why I'm writing bar. So where this phi M, so these are the elements of order M. Okay, no other elements are of order M. Okay, so you can verify that. So this is also true. So everything is true here. Every element of this finite order, right? Third is false, right? Yeah, because we have given the count, right? So this is very important group. Okay, again, I'm going to let it know because you will give the exams and you will see that in IIT JAM there are questions from the group Q modulo Z. In every exam, if you will, if you will solving previous year exams of any exam, then there must be some question from Q modulo Z somewhere in the some year. I can say that. Okay, you can see NBHM, you can see CMI, you can see IITJM, CSRNet, GATE, anything. There must be some question in some air from Q modulo Z. Okay, so whenever you will be interviewed, you might have, I mean, you might face the questions from this group. Okay, so it is very important. What is the property of Q modulo Z? That it is an infinite group and every element inside it has finite order, and it has an interesting subgroup. What I someone told just, right? So it has also an interesting property. Okay, so yeah. Now let me ask you a question. Okay, now you have to answer it as I always ask you interesting question after some question. So what do you think about the are these groups isomorphic? Q and Q cross Z. Question 1. Okay. Are these isomorphic? Just raise your hand, okay? If you immediately come to know, oh yeah, they are not isomorphic. Oh, they are isomorphic. So just raise your hand. I will give you 1 minute at least to think about this. So there is another question which is coming after this. Raise your hand first. Then I will ask randomly to someone. Are these isomorphic? Yeah, try everyone. And don't hesitate to raise your hand, okay? You should not afraid of being incorrect, okay? You can say anything, right? Sometimes a lot of students afraid of being incorrect, right? So what happens if we are incorrect? It's okay if you are incorrect, okay? Don't worry. Mathematics is something we might be incorrect a lot of times, right? So I think someone is unmuted. Okay. So can you check your? I mean, and that one does not know also. I think so. Okay, so could you not think about it? Let me give you some hint. Okay, so what are you thinking about? You are thinking, right? That is there some elements which has finite order here, and that element, I mean, there are two elements of finite order. If what are the number of elements which has finite order here, something like that, right? But you will not find something like that because here is only one element of finite order, and here is you have also only one element of finite order, right? That will not help you. You can use something else. Okay, so Ria, tell me.
Sir, we
Where
draw a map from Q cross Z to Q by
no, first
isomorphic.
first answer. Okay,
Isom
so right. Yeah, so so anyone else?
Sir, sorry, not
you can
isomorphic because it
not as
isomorphic to
yeah,
Q by Z.
if you think that Q by Z means
सर ऊपर का जो है Q by Z.
हाँ, कौन सा वाला आइसोमॉर्फिक होगा?
Q cross Z.
No, it has all the non-identity element of it are infinite order. Okay, you can think about it. Yeah. So someone else want to answer? Okay, so let me give you a hint. Okay, so what hint I can give you? That just see what are the finitely generated groups of these two groups, finitely generated groups. This is the hint for you. Okay. Finitely generated subgroup of Q is cyclic, right? Every finitely generated subgroup of Q is cyclic. Yeah, Devbrat, please.
In Q, every finitely generated group is cyclic, but in Q cross Z, if we generated a finitely generated group, then it is not cyclic, like
So give me
0,
an
1.
example. Okay, every finitely generated subgroup is cyclic. So which one is not cyclic?
In Q cross Z,
You can just
0,
take Z cross Z,
1
right?
and 1. Yes, 1,
Finitely,
0 and 0, 1 से जो generate होता है.
okay, ठीक है. Finitely generated, but not cyclic, right? So hope you all know that it is not cyclic. Okay, so the groups are not. I mean, isomorphic. Okay, let me ask you another question. So these are the group of positive real numbers, and R cross Z are isomorphic or not? Think about it, right? We are learning. We all are learning. So we must think about it. Okay. Everyone try. Try. If you don't have courage to try, then how will you solve the questions in exam, right? I don't expect that you answer, but still you should try. I will give you some hint then. The thing what we used in last is not working, right? Now what can you do? Then I will give you some hint, okay? So whenever you have given two groups, right, G1 and G2, so what do you try? You try the elements of some specific order which are here but not here. Then also you see the elements in center, okay? You see the number of subgroups, okay? To prove that if there is something different, then they will not be isomorphic, right? So, but that kind of thing not going to work. Okay, you can check. So just try to think something special. Okay, some special thing about R. And that special thing in common in R, Q, and C. Okay, some special property of R, Q, and C. Yeah, some Sagni, you raised the hand. So what do you think that they are isomorphic?
R is a divisible group. But R
So
plus
you
Z
should
is,
not go so far.
I mean,
Okay.
we can look at the homomorphic images. So R plus Z has finite homomorphic image.
Why it has a finite homomorphic image?
What? Say for example, R cross 2Z. When I take its quotient with R cross 2Z, then we get a finite,
Right,
but we won't get
right,
such a homomorphic image
right.
for
Very
R.
good. Yeah, good. Yeah, that's what I want. Why I expected. Good. So what we see here that R has no proper subgroups of finite index, right? Has no proper subgroups of finite index, right? You know, I think this, right? Because if you take, suppose that some subgroup is finite, then its order is finite, right? Say n, then you get nr inside H, right? This is well-known property of the cosine group. So then you see that nr is inside H, right? But nr is again R, so R is inside H, right? So R must be equal to H then. So it does not have proper subgroups of finite index. On the other hand, if you quotient it by this proper subgroup, this comes out to be R, right? And this is isomorphic to Z. Or to Z. It has a proper subgroup of finite index. So they are not isomorphic. Okay. So try to look at the groups of finite index sometimes also to prove that the groups are not isomorphic. Okay. So whenever you have given two groups, then you have to look some specific properties of the group. Okay. There is some specific property on group G1, but this is not in G2. Okay. Right. So think about this one. Okay, so I will give you this question later. So come to the next question now. Yeah, this is question from CMI 2024. Okay, this might be helpful for you. Don't think that if this is a question for CMI, okay, so why are we solving that? No, it's I mean important. Okay, no, the first one is not from CMI. This one is from CMI. Okay, let me solve it first, then I will come back to this. Okay, so this is from TIFR. Okay, so now you have this question. Okay, so now we would like to solve it. Okay, so see what questions say. Which of the following statements are true? Every prime ideal of a finite commutative ring with unity is maximal. Okay, so yes, this is true. See why this is true? Because suppose you have a P which is prime ideal, then R modulo P is an finite integral domain, right? Finite integral domain. Finite integral domain, right? But a finite integral domain is, say someone,
A field.
finite, yeah, is a field. But if this is a field, then what happens? Quotient ring is field.
P becomes maximal.
It is maximal.
Right. So P is maximal. Okay. So that's true. Okay. So now about the second one. A commutative ring with unity whose set of all ideals is countably infinite is necessarily a countable ring. So what it says that you have a commutative ring with unity R, a set of all ideals. It has countably infinite ideals. Okay, countably infinite ideals. You know what does it mean? Countably infinite. So then the ring must be countable ring. So try to think about it. If you come to know about a counter example or you think that this is true, raise your hand. Okay. So at least you should think for a moment. Okay. So first, okay, Sagnik, so you have thought about it. So what do you think? This is true statement or false? First, let me
This
know
is
about it.
false. We can
Oh,
take a uncountable
okay,
field.
okay, right. You did not to tell. Okay.
Hmm?
Yeah, I just want to know that it is false or true. You said false, right?
Yes.
Okay. Let's to think also. Okay. See. First, try to counter it. If you want to counter it, just try to think about a ring, okay, which is uncountable. For example, R is uncountable, right? So, but it has finitely many ideas, okay? But we want countably infinite ideas. So what can we do? We just take the product of this with this, and we know that the ideals of the product are like this, right? MZ or R MZ, M belongs to Z. Okay, right? The ideals of the ring A cross B are of the form I1 cross I2, right? Where I1 is A cross B, where I1 is ideal of A and I2 is ideal of B, right? I have used that thing. So here we see that a set of all ideals is countable, right? Because these are countable ideals. This set is countable and this set is also countable, right? So their union is countable. But our ring is not countable, right? So that's why this statement is false. Okay. First one is true, second one is false. Now the C. Let R be a unique factorization domain and K is K be its a field of fractions. Okay. There exists an irreducible element alpha in R and an element beta such that beta is square equal to alpha. Okay. So what do you think about it? It means that some irreducible element has a square root. Just try to find, start from basic example, okay? In place of R, take Z, okay? So then what is the field of fractions? Field of fractions is Q, right? So what it says that there exists an irreducible element. What are the irreducible element of Z? They are prime numbers, right? B, they are just prime numbers like that. Plus minus 2, plus minus 3, dot, dot, dot. So what do you think about it now? Do you have some element whose square is prime number in Q? No, right? Do you have some element whose square is 2? Do you have some element whose square is 3? In your K, Q? No, right? In this way, no prime has a square root, right? So this is also a false statement, right? Now the interesting option comes that every sovereign R which is between Z and Q has infinitely many prime ideals. Okay, I had asked you also such kind of question in previous 2 lectures. So what do you think about it? That option D, suppose R is a subring which is not equal to Q, not equal to Z, has infinitely many prime ideals always. So first you should know some subring, okay, between Z and Q. Then you will be able to know about the Ideals. Could you think of some ring which has not infinitely many prime ideals? Okay, let me tell you. Okay, so this ring we have, let me denote it by this. Okay, ZP, M by N, M and N in our Z, and P divides N. P is fixed. Okay, this is a subring you can convert and home. So P does not P does not divides N. Okay, rather P, I have written P divides N. Okay, P is a prime, you can take 2. So what are the units? This is a PID. Okay, you can prove that at home. This is a PID every time. Note that. So this is a PID. So can you tell me the set of units of this ring? What will be unit? What are the units in this? To see that some element is unit, what you have to do? Say some element x m by n is unit, there exists a y so that this becomes n. Then y should be of the form you will get. So let me know. What is the set of all units?
P does not divide M.
P does not divide M. Right. M by N, this first must be in ZP, and P does not divide M. Right. So a set of all non-units. Which are not unit is equal to that's easy now because you have already determined what are the set of units. What is the set of units? Set of all non-units is
P divides M.
right, M by N inside ZP such that P divides M. Okay, so now is this an ideal? Ideal? Ideal of your ring, given ring. How do you prove some
Yes.
subset is the ideal? Yeah, this is the ideal, right? Okay, ideal. So if this is the ideal, then what we have seen here, then this must be maximal. Okay, let me name it M. So M is maximal, unique maximal, by the way. Why unique maximal? Let me tell you. Okay, suppose you have some another ideal. Okay, then I. Okay, by the way, it is unique maximal ideal. See, why? Because if you take some element A, that must not be in M, but this is in I. Then the ideal generated by inside A, but A is a unit, right? Because it is not in M. So this becomes R. Okay, so this is unique ideal. Any element outside M will generate. This is a unique maximal ideal rather. Okay, not unique ideal. Is it okay? Because any, how do you prove that it's a maximal? Suppose that it is like this. Okay, I mean something is between M and R. Then prove that what I have told you, use that. Okay, so you get that it has unique maximal ideal, and in a PID, every non-zero prime ideal is maximal. So 0 and M are only prime ideals. Only prime ideals of ZP. Okay, so keep this example in mind. Okay, until you don't read commutative algebra. when you will read about commutative algebra, I mean, when you will having this course, then you will learn it. Okay, this is localization of some set. So what is localization? You will learn later. Okay, so see, once you will go to TFR, then definitely you will be learning in the algebra course. Okay, so see, now come to the next question of TIFR. So yeah. So after that, this I will ask you a question, okay? So what does this say? That there exists a continuous function f r to r such that f of q lies inside q complement, and q complement, the image of q complement lies inside q. So this suppose exists, okay? Let us suppose that exists. So this implies f is non-constant, right? First of all, the above condition implies that f is non-constant, because at rational point it will take irrational value, and at irrational points it will take rational value. At least it is taking two values, so it is a non-constant function, non-constant continuous function. So continuous function, and a non-constant continuous function has uncountable range, right? Let me tell you why, okay? Suppose your function takes the value r, say it is rational, and takes the value alpha. Say they are like this, okay? Alpha is irrational, because you know that at least function will take some irrational value and some rational value, or they might be like this also. Then because of the continuity of function, every value between r and alpha will be taken, right? Or in alpha r. But you know that every interval is uncountable. So f will take uncountably many values. Okay, that's why it must have uncountable range. But what do we see here? The range of fr is this, right? Q and union Q complement, right? And this is equal to fq union fq complement, right? But both are give these both sets are countable. Why? Because fq, image of a countable set, must be countable, right? The image of a countable set must be countable, right? Because you have at least countable elements in the image. Okay, and the image of this, I mean q complement contained in q, so it must be countable also. The image of q sets are both are countable. So what do you think about their union? Countable, right? Countable, which is contradiction, right? So this is a contradiction. Okay, what does it mean? That there does not exist a function satisfying the given properties, which is continuous. Okay, right? So shall we move to the next? So I think you should try this question first. Okay. Okay, by the way, I want to ask you something here, because I did not ask you a question. Okay, very nice question from the continuity. Okay, suppose f r to r continuous function. Okay, continuous function satisfying f(x) equal to f of x square for all x in R. So what can you say about f? Okay, you do not have to think it here, think it about at home. Okay, can you say something about specific about f? Okay, so let's move to the next question. What does it say? There exists an injective ring homomorphism. It is same like what we saw in the last question, where we were dealing with Z2 cross Z2 and the quotient ring, right? And we are trying to find that if there exists a group homomorphism from Z2 cross Z2 to the unit group of this ring, right? So this also asks something like that. There exists an injective ring homomorphism from the product ring R cross R. Okay, this is a very nice question. Okay, see, everyone will able to understand it. Okay, don't worry if you have not, I have to also keep in mind that there are students who have not covered much of syllabus. Okay, don't worry, you will also understand it. Okay, see, so what that real numbers, right? And the Cartesian product also. This also is a ring. So ring homomorphism just means that a homomorphism which preserves the composition, which preserves multiplication and addition. Preserving means, suppose that you have two elements from here, okay, say alpha and beta. If you take, say, image of alpha is f alpha and image of beta is f beta, right? Then image of alpha plus beta must be equal to image of f, this must be equal to f alpha plus f beta. That's what. In this way, same multiplication. Multiplication is also preserved. Okay. So that is a ring homomorphism. And this is a collection of all continuous functions. They are added pointwise and multiplied pointwise. Okay. So what we are asked that is there an injective ring homomorphism from R cross R to CR? So yeah, think about it. So why I'm asking you, why I'm saying you that you should think, because this is similar question. Okay. What we did last time. Okay, let me tell you. Let me give you a hint. Do you know about the idea? Sagnis, you have thought about it. Okay. So yeah,
I was
let me
going to
know,
say
is this possible or not first?
It's
What
not
you are going
possible.
to do?
I was also
It's
thinking
not.
about idempotents. There are many idempotents,
Right.
but in CR
Right,
there
right,
are
right. Right. Okay, good. So say that some homomorphism is there. Okay. Assume injective homomorphism. Injective homomorphism. Okay. So then what happens that idempotent, if you have some idempotent element, a idempotent, a ring homomorphism also preserve idempotent element. Okay, if you have idempotent element, then its image must be idempotent. Then phi of a is also idempotent. Idempotent just means when you square it and you get the same element. Okay, so see, now how many idempotents are there? Okay, so how many elements are there when you square them and you get the same element? There are 4, right? 4 idempotents. So we have phi 0. These are distinct, okay, because of the injectiveness. Phi 1 0, phi of 0 1, and phi of 1 1 are idempotent in R idempotent in CR. Okay, these elements must be idempotent in CR. So, but what we see, let's find that how many idempotent elements are there. Okay, so suppose some F is idempotent, then F square equal to F, right? That means that F of X into F of X equal to Fx for all X in R, right? Because if two functions are equal, then they will be equal, give the equal value at each X, right? So from here we get that Fx into Fx minus 1 equal to 0. So it says that Fx is equal to 0 or 1. Okay, for all X. But because F is continuous, it cannot take 0 and 1, 0 and 1, right? Either it will take every time 0 or it will be every time 1, right? Because the image of a continuous function would be either singleton or it would be uncountable, right? So no function can take 0 and 1, 0 and 1, right? Then the values between 0 and 1 should be taken because of the continuity of F. Okay, so we get that F is identically 0 or F is identically 1. And there are only two idempotent. So this is contradiction. But what did we get about that contradiction? Okay, here we see that there must be 4 idempotent element. If such a at least 4 idempotent elements. If such an injective homomorphism exists, but this is not possible because there are only 2 idempotent elements in this ring. Okay, so in this way we have solved this question. It means this is a false statement. Okay, so now I ask you a question. Okay, so can you give me an example of a ring? Rather, example of a ring, right? Say that is vector space also. Okay, you can just say like R and R is a ring. Okay, can you give me an example of a homomorphism which is group homomorphism? I mean, which is additive homomorphism but not multiplicative. I mean, which does not preserve composition, does not preserve multiplication. Right? R is a ring, and you are asked to find an example of a group homomorphism which is not a ring homomorphism. Can you find that? It's not a difficult question. I'm just asking to see whether you can answer it or not. Think about the basic examples and you will get to know.
It should be vector space also.
No, it shouldn't. Needn't.
Then we can say 2z and 3z are okay. Sorry, R and R are same.
Right. You can extend them. Yes, 2z and 3z, then just extend them to make the same. Right. So go to Z and Z. Can you find a homomorphism, group homomorphism from Z to Z, which is not a ring homomorphism? Right, you can find. Okay, so see. Okay, so for today I will stop early. Okay, so tomorrow we will be discussing questions. Okay, by the way, I want to discuss something. Okay, wait, what I said. After that, we will say goodbye to each other. So this question is very, very interesting. Okay, you will, if you will feel the solace, I mean, if you will feel what beauty of this question, then you will really amazed. Okay, astonished. So this is very interesting question, really. So you might feel that you cannot solve it, okay, but definitely if you will try, you will be able to solve it. First, let me tell. So this says that if C be the subset of, this is question of NBHM, and believe me, such kind of question can be asked in TIFR, okay? Because I have seen that in TIFR they ask questions from the sequences of integrals, okay, involving continuous functions. So C be the subset of real valued continuous functions fx on closed interval 0, 1, closed interval -1 and 1, such that fx is greater than equal to 0. And what is given to us? That the limit sup of this sequence, okay, -1 to 1 and tending to infinity, fx and dx is less than infinite. Okay, this is given. So what is the image of C in R under the map? Okay, so this collection is a subset of all real valued continuous functions which are not the closed interval -1 to 1. So you send every function f from here to this integral, right? Because a continuous function is integrable. So this is well-defined real number, right? So what I have written here is a well-defined real, right? So you have to tell what. Okay, just try once. Okay, I will give you at least 4 minutes. If you will solve it, I would really be impressed. Okay, 4 minutes, 3 or 4 minutes. Try it. This is the last question of this session today. So, oh, by the way, tomorrow I would be solving one full paper. Okay. But I don't think that we would be able to cover a full paper in within 1.5 hours. But I will take one paper only tomorrow. Okay, and I will give you tomorrow some notes also by which you can complete the. You listen. Remind me. Okay. About it, I will give you notes where I have solved the exams completely. They are handwritten notes, so you can look at the solutions. Okay, because what I said that it's not possible to cover all the. I had already given you the references of video where you can watch the solutions, but I would also like to say with you some handwritten notes, okay, so that you can cover the previous year problems early, right? Because you don't have too much time. So please remind me, okay, if I forget about that. So yeah, tomorrow I would like to share that. Not only that, but I would like to also uh, some material which will be really helpful for you within these 7 days. But definitely tomorrow I will be sharing that. So yeah, think about this. I will be giving you 3 and 4 minutes, and yeah, please think about it. And I would discuss it in detail, okay? Everyone will understand it. Don't worry, I will not go fast. This is one of the questions which I like very much. Okay, so see, try to guess first what can be the image, okay? First, you should have a strong guess, right? Then you would be able to, you will try to prove that. First, think about the guess. At least you should guess what can be the image. Or you can say that at least this must inside image. This much. This set must lie inside image. Okay? That much you should do, right? Okay, I will ask you that if someone of you would be, someone of you is able to find some interval which is contained in the image, at least that you can say that, okay, sir, this interval must be in the image.
So 0 to half.
Yeah, someone.
Sir, 0 to half, 1/2.
0 to half. Okay, 0 to half must be there. Okay, sir, can it be enlarged? 0 to 1, 0 to 2. Okay, Lucas. Yes.
Definitely.
So 0 to 2.
Okay. Okay, 0 to 2 must be inside the image. Very good. So what do you think? Is it exactly 0 to 2, or we can
Yes,
have
sir.
some other elements?
Like we can check
So
the maximum of this function. I mean, f. And then if the maximum is greater than 1, I claim that it cannot be greater than 1. And if it's greater than 1, then this supremum will not be, this limit will not be finite.
yeah, very good, very good, very good. Right. So how did you do that? What did you use? Just let me know. I would not ask for the full solution. So yeah, you are right. So if it takes value greater than 1 at some point, what happens then?
This limit will be like infinite. Limit of supremum, this would be infinite.
Did you use the continuity?
Sir, we can make a bound, no? Like -1 to f. We can get a lower bound like with that
right.
Something like that. Sir.
So yeah, your idea is right. Okay, so let me write it. Very good. So
sir, may I do it the epsilon delta way?
Yeah, Dhruv, what did you say?
Sir, that proof which you are saying, can I say it in that epsilon delta manner?
Yeah, that would use the neighborhood property. But you can just say the result, okay? You don't need to involve epsilon and deltas.
There will, if we have some number which is greater than 1, so then there will be a neighborhood which is greater than 1. And then in that neighborhood,
there will be a neighborhood in which fx must be greater than, right?
The integral over that neighborhood will be greater than 1. So then we can raise that to n and it will go to infinity. Therefore, it cannot be greater than 1.
But that would be, I think, greater than an equal, because the limit can be equal, right? Because if you have two sequences yn, and if you yn and xn satisfying this, but the limit may be equal, right? Did you get what I'm saying?
Yes, sir.
So how do we deal with that situation? Let me know. But your idea is very correct. Okay.
Currently, I just took greater to just avoid that.
Yeah, right. So see, what you have given. You have continuous functions from this interval, right? Defined on this interval. And you are asked to find the image of this set, but you have to take the functions which satisfy this one, okay? So at least this, let me draw a rectangle here, okay? Okay. So this point is, this line is y equal to 1, okay? Right? So now just try to guess what is the image, because we should have a guess first, okay? Then we would see that if this is true. So see, if I take the constant function fx equal to 0, or you can just say r, okay? First, let me take 1, okay? 1 satisfies everything, right? It is greater than equal to 0. And if you raise the power n, then what comes out to be this thing? See here. So it is greater than equal to 0. And if you find this integral in this case, this comes out to be 2, right? Put just 1 there and evaluate the integral. It comes out to be 2, right? At least 2 should be there. In the same way, you can take any number, right? Between this, then you get that. What did you get? So if I take fx equal to this constant function where r is that, r is between this, then you see that this happens, right? Dx, okay, this thing is equal to 2 times Rn, and as n tends to infinity, this goes to 0. Hence, the limit supremum is also 0, which is less than infinity. Okay, right? Yes or no? Or do I need to write this? That if this sequence is this, right, as n tends to infinity, then this goes to 0, right? So its limit supremum is, so what I said that I will solve it in detail. So its limit supremum is finite. Okay, this implies that Rn dx less than finite. So what do we get? At least this number must be there, right? The if you find the integral r minus 1 to 1 r dx, this comes out to be 2r. At least 2r must be in the image. Okay, let me name the image set Im. Okay, just denoted by I. Okay, so 2r for each r between this. So that means that at least this interval is there. Right. Now the crucial part comes. Okay. So what happens whenever you have some, function whose graph, moves here only inside this, rectangle, then it's fine. Then its area is not going to be greater than 2, right? Can you see that if some graph of some function inside this rectangle, then the area, this area, okay, which is gradually being read, so is less than 2, right? Yes or no? Right? Because the rectangle is of area 2. Okay. So what happens if some function's graph goes outside this rectangle? What happens? See, suppose to understand, suppose that this happens, right? So now just think roughly, okay, when you will square this element, then at this point, right, at this point, it takes value, it takes value this at 0. Then when you will square, it will be here, okay, something like that. I'm not saying that this is just the graph of square, just think that it will be like that. But when you reach power, then the see, area might go to infinity, right? This is our just rough guess, okay? I'm not saying that this just the graph of f square look like that, right? So now let's try to prove our guess that if a graph of some element, if some function takes value greater than 1, then it is not going to satisfy this thing. Okay. Okay, let's prove it. Suppose, okay. So in this way, you approach the solution. Okay, this is natural approach, right? We are not doing something very different. No one can say that, oh, how do I solve this problem? How do I think about it? Everything is natural, right? Okay, so in this way, you should first you guess the, our guess is that this can be the image. Okay, now we will try to prove our guess. So what happens that
Sir, why the range of the function is cannot be greater than 1?
Range of the function cannot be greater than 1 means which function? Oh, I mean to say, what do I mean to say? The function f cannot take value greater than f. If it takes the value greater than 1, so greater than 1, if it at some point takes the value greater than 1, then this is not going to satisfy. Okay, I'm going to prove it. So what I tell you roughly that the area bounded by that curve would, if you find the area, right, this sequence, say f square, you are finding the area which f cover, the bounded by the graph of f, and then you find the area which is bounded about the graph of f square, and so on. I mean to say that this would keep on increasing. Okay. So I roughly told you. Okay, let me prove it. Okay. So see. So why it cannot take? So suppose that f takes the value 1 at some point. Okay, at some point, right? So we have by neighborhood property takes the value greater than 1, rather greater than 1. Okay, 1. Then by neighborhood property, NBD property, you must have seen this in your real analysis course, that fx remains greater than and equal to r on r is some greater number than r. Okay, r is some number greater than 1. Okay, on I r, right, on some interval. So far, do you agree? This happens, right? Because of the continuity of function. Okay. So now see, if you give the power n, then this happens. Everything is positive, right? And you know from the Riemann integral that this thing first would be, okay. So, so let's integrate it in this interval, IR. Okay. Then because IR must be inside this interval, right? So fx to the power n dx, right? So far it's clear. Do you agree with me? Everyone understand this, right? Okay. So see, now forget about this one in between. Okay. Okay, but I will send you the notes, then you will see that where that goes. Okay, let me write it again. You get this, right? Now integrate on both sides. What do you get? You do get that this thing greater than r to the power n and IR, right? IR. Yes or no? IR is the, sorry, length of the interval. Okay. Rn, and Rn will come out from the interval, and you have this. Okay. This is just equal to the length of interval, right? So what happens that we get this, right? So now take n tends to infinity, you get, okay. This implies limit n tending to infinity -1 to 1 fx and dx is infinity. So the supremum is not less, limit supremum is not less than infinity. Okay. So if our sum function takes the value greater than 1, then this not comes under this category. Okay. So we do not have to think about the functions which takes value greater than 1. So now what happens is that any function which satisfies this lies inside this rectangle. Its graph lies inside that rectangle, and the area of, we need to find this, right? Area bounded by the graph of that interval is must be less than equal to 2, right? So I mean that will not, I mean that will give you some point inside this interval. Okay, so that's why the image is exactly the closed interval 0, 2. Do you understand this? Is it clear? Yeah, this is one of the nicest questions. So yeah, in this way we end this session. Okay, I did not ask you a lot of questions today, so because I have already asked you too much questions and you must be solving them at home. So I think it's time to stop now, and we will be discussing some I think I will pick some specific paper, but I would say that if you have some specific problems which you could not solve in the TIFR exam, be it of any area, be it of any year, then you can send it to me. Okay, I would also take that problem on tomorrow's session. Okay, right? After that session, we will have a mock test. Okay, so yeah. And one thing I wanted to say something, yeah. Oh, but I should say that at the first beginning of the this session, actually, some of the in YouTube, I was saying that some of the student was asking that how can we join these sessions live? So you can just text me in Telegram, or you can just, then I will send you the link of, or I will paste the link in the YouTube, and I will ask sir to also paste the link of the these sessions in the YouTube. Yeah. Okay, so I should stop here. So yeah, someone asked that. Yeah, 1 minute, sir. Someone asked that why the function cannot take the value greater than 1. Is it clear to you now that why it cannot take?
Yes, sir. Yes, sir.
Yeah. Okay. So, fine. So do you have any questions? Anyone?
Sir.
Yeah.
Sir, if the question when he asked for a group homomorphism not preserving multiplication.
Okay, so you did that?
No, I wanted to ask, why does 2x not work?
Oh, I did not say that that would not work. That can work.
I was thinking all ax will work.
Yeah, definitely. If they are not idempotent, if A is not idempotent, right?
Yes.
Yeah, yeah, definitely. Yeah, right. Your answer is right. Okay. So, okay, let me pose a question here. Okay, so you have to, okay, let me give you some questions. Okay, so see, this q root m, you know about this. M is square free. Okay, M and N are square free. Okay, just give me some specific examples here. 30 and 2 root 15. So I will ask you tomorrow that are these isomorphic as vector spaces over Q? Are these isomorphic as fields? And are these isomorphic as groups? Okay, so I will ask it tomorrow. This is the question for tomorrow. Okay, so I should we should say goodbye to each other. Yeah, right. So let me. Yeah.
Okay, thank you, Lalit.
Okay, so by the way, I want to send this notes to all of you because a lot of students were asking me to. I will send it to sir. They will send in the group also, and I will also send in that group Telegram group also. Okay, so you'll find it.
Yeah, Lalit, if you can share it as a PDF, we can attach it.
Yeah, definitely. I will be sharing it as a PDF. Please share it to all the students.
Sure.
Okay,
I will share.
So
to
yeah, definitely.
So
I will share it just after this session.
Okay, so dear participants, if any of you would like to share a feedback on today's session, you can make it now. Anyone want to comment or want to ask or want to add something? Yeah, yes. I think someone is trying to speak. I don't know. Yeah, some reactions are sharing.
Yeah, but we don't know that who is reacted. Okay, who reacted?
Okay, anyway, we can wind up today's session now. Okay, as you told, tomorrow we are having more discussions. So let us wait for that. So yeah. Okay, bye everyone.
Bye everyone. I think we should stop the recording. Yeah. Okay.